I'm a registered dietitian and the food data curator here with Wolfram Research. Today, we're going to be talking about how to compute, analyze, and visualize food and nutrition data in Wolfram Language. I think it's a topic, one of my favorite topics is food, and I think for many people as well. These are some of the topics we'll be covering today. We'll be talking about different ways to query for nutrition data. We'll talk about the nutrition facts label, as well as some fast and easy ways to do nutrition analysis with food resource functions. These are really handy ways to get quite a bit of nutrition data very efficiently. And then we're going to talk about one of my favorite topics is food chemistry, and I'm looking forward to sharing with you why food chemistry is such a favorite topic of mine. So I first want to talk about interpreter, which is a really wonderful functionality we have in Wolfram Language to retrieve food data. Interpreter is, we use that to retrieve what we call the implicit entity for a food. For example, you can see my example here of steamed broccoli. So this implicit entity holds all of the data points for the nutrition data for steamed broccoli in the Wolfram knowledge base. And we have a knowledge base of almost 500,000 foods. And so all of the entities, as you can see, this steamed broccoli that we retrieved with interpreter very efficiently has all the explicit branded foods for steamed broccoli that are within that implicit entity. And so you can see all those data points are pulled together and compiled to give you the very accurate nutrition data for that particular implicit entity of the steamed broccoli. Another way to retrieve food, the food nutrition data within the Wolfram knowledge base is with natural language. And so the wonderful thing about natural language, you just type your query, use your control equals to open your input box, and then type your query in natural language and evaluate that. And you'll see that you get, in this example, I want to know the potassium in 6 ounces of tomato sauce. And you can see that I get that both, I can get that in scientific notation or in numerical form to get that volume of that amount of that particular nutrient for that particular implicit entity of tomato sauce. So you can use interpreter or you can use natural language to query all that data in the Wolfram knowledge base that represents almost 500,000 foods, which is a fantastic and accurate and reliable data that we've curated from a wide range of reliable sources, including the USDA and the European Food Information Database. Another really wonderful functionality we have is to quickly produce a nutrition label just with the nutrition label property. For example, here, now this, as you know, the nutrition label gives you the nutrient composition of a food. You'll see it on all of your packaged foods and the percent of the recommended daily values that food provides. And you can see in this case, I've simply asked for a nutrition label for a single serving of tofu, and it's quickly retrieved all of that data. Looking at that nutrition facts label. Now, another thing we talked about, I talked about using some resource functions. We want to cover some of my favorites. We've got about a dozen functions in the Wolfram function repository that cover a host of standalone functions. And so here's a few of my favorites. So do visit the Wolfram function repository. Just type in the word food and you'll see all the many functions we've designed for retrieving, recipes and nutrients. Here's a few that I wanted to highlight today. For example, nutrient comparison bar chart. And so this gives you quickly all of the macronutrients for a list of foods. For example, you can see in my example here, I'm asking for these high protein foods, the eggs, the peanut butter, chicken, beef, etc. And what it nutrient comparison bar chart will do very quickly and efficiently, it will bring back your calories, your protein, your carbs, your fat, your fiber, and unfortunately, there's my favorite, one of my favorites, peanut butter, which is very high, the highest in calories and fat. But so this is a really nice, efficient way to compare a list of foods for these macronutrients. Another way we showed the nutrition label. Another way to quickly retrieve these highly requested nutrients, these very popular nutrients, as well as those percent daily values, is just with the nutrition label data resource function. And that is, you can see here, it gives you just the straight up data that you can use to manipulate in all kinds of ways, such as do visualizations, bar charts and so forth based on this. So you can see I've asked for the nutrition label data for 3 ounces of beef, and I get not only all those nutrients, the absolute, how much calcium, how much zinc, how much magnesium, but I'm also getting what that percent daily value based on an average 2,000 calorie a day, how much that particular serving of that particular food will provide. So that's a quick way to retrieve a lot of data. Another really, really robust function I wanted to share with you is our nutrition report resource function. And you can see I've just given it a recipe for a Dijon vinaigrette here. And by the default output for nutrition report is a data set. And so you can see we get those macronutrients for each of those ingredients. There's lots of options with nutrition report. I want to highlight a few. Our newest option with the nutrition report function is the tabular. You can create a tabular object. That's been recently added, which is a really wonderful new feature of nutrition report. Also, I like this one a lot. It was outputting an ASCII table. You can request an ASCII table to see these macronutrients for, say, a recipe. And it's also, as you can see, it's going to tally the absolute total nutrition for that recipe. And in this case, this Dijon vinaigrette, I'm getting 620 calories, 70 grams of fat, etc. And so this is a good way to get those total macronutrient values for a complete set of ingredients or a complete recipe. Next one I want to go through, which is really an interesting one. As you know, as you may know, the body needs 20 different amino acids for it to function properly, and these amino acids combine in different ways to build proteins that we need for health. And so we have this amino acids bar chart, which is a wonderful resource function. And what you do is just put the foods that you're interested in terms of the amino acid content in your foods. And then you're going to get a drop down list of all 20 amino acids. So you can see, I can quickly and easily choose a variety of amino acids to make a comparison of my list of foods. In this case, I'm using these protein sources. And then also another function you can do is you can, pare that down, just take, uncheck some boxes, and it will quickly change that. So this is a really good way to quickly make comparisons across a list of foods for a variety of amino acids. So highly recommend that. And and also you'll see if you can do a 3D version. So you can display the data like we just did, but in 3D, there's a 3D option. And then also a really nice feature is if you choose all in the drop-down box, you'll get a comprehensive 3D bar chart of all the amino acids for those foods listed. So that's really helpful. And you can see in this case, I'm using those high fatty fish, salmon, mackerel, and tuna as the example in this particular case. So I do recommend going to the Wolfram function repository and pulling this particular amino acids bar chart. There's lots more examples in there for each of these. Speaking of, I'm going to stay on amino acids just for another minute here. There are, of those 20 amino acids, there are 9 that our body cannot synthesize on its own. And we need those amino acids for our physiological needs. And so these are called essential amino acids. And that's because they must be supplied by those protein foods in our diet. So they're essential to our diet, right? And so we've also created a resource function here where you can just pull the essential amino acids quickly and efficiently for the foods listed. So in this case, you can see I've said, let's compare chicken and turkey and the essential amino acids in chicken and turkey and make a comparison. Interesting here, how tryptophan has the reputation. You can see that the tryptophan here in the yellow. Turkey always has the reputation of being the one in the food with all the tryptophan that makes us sleepy after a holiday meal. But as you can see, interestingly enough, chicken is actually right up there with turkey in terms of tryptophan. So that's kind of an interesting side note on our essential amino acids there. So moving on, this is one of my favorite topics, I have to tell you, in terms of food, and it's food chemistry. And hopefully, I want to share with you why I love this topic, because molecular structure, molecular structure is key to our foods, and we don't really think about it that often, but the molecular structure of the chemicals in our foods are absolutely key to determining the texture, the aroma, the stability, the flavor, and the nutrition of our foods. And that's why I think it's such a fascinating topic. Our chemistry team has recently introduced this new function called molecule feature distance function. And it's also known as a molecule fingerprint distance. And this function lets you compute the dissimilarities between two molecules. So this is really handy. So if it's on a scale of 0 to 1. So a smaller distance is higher similarity, a larger distance is greater dissimilarity. And so the interesting thing is nutrients and the other chemicals that compose our foods lend themselves to pairs, such as omega-3 and omega-6 fatty acids. And so that's why this new function is really perfect for looking at food chemistry. So I want to look at a few of our favorite molecules. Speaking of omega-3 and omega-6 fatty acids. So if we look at this molecule feature distance, we can see it's only 0.2, right? So that tells us that linoleic acid and alpha-linolenic acid molecules are very similar in their molecular structure because they only have a distance of 0.2. But let me tell you the interesting thing here, that small variation in their molecular structure still makes them nutritionally distinct from one another. So linoleic acid is an omega-6 fatty acid, and it's found in plant-based oils, and then alpha-linolenic acid, that's an omega-3. And I think I wanted to look at this because just from a molecular structure, you can see that I've also, if you ever wonder why is it called omega-6? Why is it called omega-3? I hear omega-3 all the time. Well, it's because the omega-6, its first double bond is 6 carbons away from the methyl end of the chain. If you look at that linoleic acid, 6 carbons from the end. And the ALA, the omega-3 fatty acid, is just 3 carbons away from the methyl end of the chain. So I think that's fascinating just to see why are they called omega-3 and omega-6s, which we hear a lot in the news. Foods high in ALA, those are walnuts, flax seeds, and a lot of those omega-3 fatty acids are quite beneficial, as we know, for our cardiovascular health. Moving on to another, I think, a fascinating couple of molecules is we look at monounsaturated and saturated fats. So again, let's look at the oleic acid and palmitic acid because they are structurally similar. Again, 0.26 is their distance from one another. If you look at oleic acid, that's monounsaturated, right? If you look on the left, that's one double bond. And if you look at palmitic acid on the right, that's saturated, and we know that's because there's no double bonds. So the fact that this difference, that one double bond versus no double bonds, that affects both the melting point and the nutritional status of those fats in our diet. So if you think about melting point, saturated fats are solid at room temperature, right? And so that's why you can see that palmitic acid, those molecules can stack right up against each other and stay solid at room temperature. And also the difference, unfortunately, they also can stay solid in our bloodstream, right? So those saturated fats. So as you can, oleic acid is abundant. We see it's abundant in olive oil, canola oil, and then as expected, palmitic acid is found in palm oil and also animal fats. So as we know, we should choose monounsaturated fats over saturated fats to help reduce our risk of cardiovascular disease. A couple more molecules I want to take a look at. First, caffeine and theobromine. Theobromine, that's from the cacao plant, and that's found in our chocolate, right? Has a bitter taste, and it's unlike caffeine, which is theobromine has very little stimulant effect on our central nervous system. And the reason lies in the structural difference of the molecules. So if you see the molecule feature distance there, it's 0.47, so a little more dissimilarity than the ones we were just looking at. But if you look at the structure there, caffeine has 3 methyl groups and theobromine has 2. And that third methyl group on the caffeine molecules means it can more readily cross the blood-brain barrier and act on our central nervous system. And that's why theobromine has minimal effect on our central nervous system, but caffeine can cross that blood-brain barrier, which frankly in the mornings I'm quite grateful for. So for that molecular difference. Amino acid clustering tree is a great function here where we can easily and quickly take the amino acids chemicals class, add the clustering tree, and quickly see the molecule feature distance among all 20 amino acids. So this is a really, really neat way to see which amino acids are structurally similar and which are dissimilar. Next, I want to move into the National Chemistry Week. We recently had that. We recently celebrated National Chemistry Week, which was a lot of fun because the theme this year was spices. So at Wolfram, we did some great things with that during National Chemistry Week. So I want to share a few of those. So what we're going to look at here real quickly is what gives spices, turmeric, saffron, and paprika their vibrant colors, right? It's their molecular structure. And so when a molecule has a conjugated system of these alternating single and double bonds, it can absorb energy from visible light. So curcumin absorbs blue light. So there you can see there on the left, that causes turmeric to appear yellow. Crocin molecules absorb blue violet light. So that's why saffron has that orange red color. And saffron, the most expensive spice in the world, by the way. And then finally, capsanthin absorbs the green blue light, and that's the molecule that gives paprika that deep red color. And so I appreciate my wonderful colleagues on the chemistry team have highlighted this conjugating system for us in the molecule to show those alternating single and double bonds and why these spices have these beautiful vibrant colors. So I think that's a fascinating way to look at spices. Color is certainly one of their factors. Um, I want to talk about oregano and thyme. We love oregano in our pastas, thyme in our chicken, fantastic flavors and aromas. And so the monoterpenoid compounds in oregano and thyme called carvacrol and thymol, these are isomers. So which means they have, as you can see, they have the same molecular formula, but they're different. They differ in their structural arrangements. So I just think that's fascinating because I like to sort of my saying is that they make a great oregano and thyme make a great pair in both chemistry and cooking. So I think that's fascinating to look at them from that perspective. Another one I want to look at is, that burning sensation when, spicy mustard or wasabi or horseradish goes right up your nose. So that sensation is due to a very volatile group in the molecule that's of allyl isothiocyanate. The AITC, that's released when we disrupt those cells of the mustard seeds, of the wasabi, of the horseradish, when we chop it, when we grate it, or when we chew it, right? And so I think it's great what we've done here with Molecule Plot and Molecule Plot 3D is you're able to see that isothiocyanate group there on the molecule, and that's due to that causes that reaction and the volatility of that reaction, and that of course the sensation goes quickly, and then you're ready for your next bite. So I think that's a fascinating way to look at the commonality, the common structure of the mustard, wasabi, and horseradish. I want to give a sneak peek here to food physics. We're next, food chemistry. Food is a lot about chemistry, but food is a lot about physics too. So you think physics is really at the heart of cooking and baking, right? You think of all the physical transformations that happen in the kitchen every day. You're melting the butter, you're browning the bread, and so we're now introducing the principles of physics in terms of food and cooking and baking. So you'll see in Wolfram Alpha, we've introduced a food physics section in our food science examples. And so we talk about the Maillard reaction for browning, liquid surface tension for creating emulsions like mayonnaise and vinaigrettes. We talk about freezing point depression for making ice cream, viscosity of honey versus ketchup versus, how the ketchup never gets out of the bottle, viscosity. And then we're also introducing diffusion, a new formula for diffusion distance, and that impacts your brining, your marinades, as well as heat transfer, how, in terms of cooking your steaks to medium rare versus medium, etc. And even volume fraction, if you're wanting to estimate the number of jelly beans in the jar, that's going to involve volume fraction. So that's a lot of fun, and in fact, let's quickly I can look at that page real quickly and show you that. And show you those. You can see right there. So looking forward, do take a look at that on our food science examples page. So here I do want to highlight that please do go and download the slides. There's a download slides link in the notebook, I'm sorry, in the session description in the attendee hub. So I encourage everyone to please go download the slides, because the link for all of these, our documentation, Wolfram community, those links are there. Some Wolfram blogs you may be interested in, those are there as well. And so please do download the slides. And also coming soon, I want to do a quick pitch for a new Wolfram U course that is in progress. It's computational food and nutrition. It's going to be a comprehensive three-part video course from Wolfram U that we have underway. Should be coming soon. So I do want to watch this space. Do go to Wolfram U and watch for that to be introduced in the near future. So I certainly appreciate you being here today. Thank you so much. I hope you're as excited about computational food and nutrition as I am. And feel free to contact me if you have any questions. And let me just see if let's see, check the Q&A real quick. Okay, let's see. Is there a smoke point typically proportional to melting point? That's a wonderful question, and I'm going to, that would be an interesting question, because certainly I know that I don't cook with, olive oil is these low smoke points. I try to cook with the higher smoke points, but I'm thinking that's actually a wonderful question from Sean, and I wish I had the answer right off the bat. But I know olive oils in terms of the, yeah, so I will definitely look into that. And do feel free to drop me an email, and we can have some more discussion about that. It's gwilson at wolfram.com. And yes, please, Sean, do drop me a question, and we can discuss smoke point versus melting point. I'll look into that. What's my favorite food? Oh, oh my goodness, that's a tricky one. So I'm kind of a pizza fan. So and so yeah, I'd say pizzas. I'm probably pizza. I should say something like tofu probably. But so I do try to balance my foods. Oh, Bob, asking about melting point data. What about smoke point? I've been looking into, I actually have collected smoke point data from various sources. And I've been looking into maybe just adding that as if we can't get it in as a property, at least get that in as a function, like we have osmolality data in the Wolfram function repository. I'm thinking about adding a smoke point function. So I have started to collect some data for that. So let's see. So yeah, I appreciate that. But and it's a really good point about I do need to think about this smoke point. But Bob and I will look into. I bet Bob and I will look into that together. Smoke point and melting point. So I think we could do something with that. And favorite foods. Now I'm stuck on that. I just so many. But thank you so much. I appreciate it. And do download. And if there are no more questions, I'll let everybody get ready for the Innovator Award ceremony that's about to begin. Okay, Sean, thank you. Okay, thank you so much. So I'll go ahead and let everyone go, and then we look forward to seeing everyone. Enjoy the rest of the conference. Look forward to seeing everyone next year. Thank you so much.